Hello everybody. In case anybody has forgotten, my name is Paul Ralph, and today I'm going to tell you a little bit about my theory of the software development process. So, yesterday Tiro was talking about language, and Bud was talking about coupling. And I want to tell you how language interacts with coupling. So Christopher Alexander, famous architect, inventor of design patterns, he had this idea that when we decompose a system into subsystems, we want to maximize cohesion and minimize coupling. But that's not what people seem to do. What people seem to do is group things together that we have names for. And this inhibits our maximization of cohesion and minimization of coupling. For example, in a car, you might combine a seatbelt, an airbag, and crumple zones into a safety system. But a seatbelt is not physically connected to crumple zones in any way, right? They're quite remote from each other. They're not really part of the same coordinated structure. So that seems a bit odd, but we link them together because we have a word for it, safety, and to apply that label, and that label, that linguistic element, overrides our better cognition. So I want to argue that this has happened in software engineering. So if you ask somebody, what are the kind of fundamental parts of software engineering, you tend to get something along these lines. Some people will give you 6 steps, some people give you 4, but people will talk about analysis, design, implementation, testing, coding, testing. Some people will talk about deployment. Some people will separate out requirements gathering or domain engineering from analysis. But you get something like this. Now that doesn't mean they go in that order, and it doesn't mean that it's linear, but these are sort of the fundamental bits that people will talk about. But these are a bit mixed up, because programmers analyze code, and they might not be the same people who talk to stakeholders and analyze what the stakeholders say. And programmers test things, and quality assurance specialists test things, and they have to analyze things to test things. And of course, tests now are automated, so you have to design and implement the tests. And you probably have to analyze the problem to figure out what the test should be. And this links together, or lumps together, low-level design choices that are generally made by a programmer in the moment with high-level design choices that are generally made by groups of people or committees or analysts or made by assumption based on the problem that you are dealing with. And then there's kinds of testing like acceptance testing, where you sit down with the user and say, here's what we built, what do you think of this, this, and this? Which have nothing to do with unit testing and debugging, and are done by totally different people. So it seems very odd to link those things together in testing, and to link the analysis of desiderata with the analysis of code and the analysis of tests. That's not really what we mean. It doesn't, when we start talking about it in this way, we realize that, no, that can't be right. That's not what we meant. So I try to untangle these things in such a way that these different elements, the different fundamental parts of the design process would not be so entangled. So you get something more like this. And I call these sense-making, coevolution, implementation. Sense-making refers to the management literature, sort of a well-researched area in the general management organizational behavior literature, and it just means making sense of the world. Sense-making just means forming and organizing beliefs about the world. That's all. Implementation is building, but it's building and debugging and automated testing all lumped in together. And you find that in small teams, the same people are doing all this stuff anyway. So building is the low-level design decisions that the programmer makes that aren't in any specification anywhere. They're just things like, am I going to call this variable this or this? Am I going to use a queue or a stack to put this information in? This stuff often doesn't need to be prescribed up front because it's obvious in the context. The programmers can just do it. But it's still a design decision. And that's closely related to debugging and into code debugging, which is something I'll probably get into a bit later. The tricky one is coevolution. Coevolution is an observable thing. You can watch people do coevolution meetings, but if you didn't know the word, you wouldn't know what to call it. So coevolution is when you have ideas about the problem and ideas about the thing you're going to build, and you oscillate between them. This is a very well researched idea in the interdisciplinary design literature, Nigel Cross, Donald Shaw, and that crowd. And what they observe is that designers will often have two different diagrams drawn on a whiteboard, informal diagrams. And one kind of represents the problem domain, and one kind of represents the solution candidate we're dealing with. And as they improve the solution candidate, they realize that they've misunderstood something about the domain. And they run back and say, wait, no, this is wrong, we have to change that. But then that triggers redesign. It triggers new ideas about the context. And they run back, or about the design artifact. And run back and say, well, no, now that we've realized that, this architecture no longer makes sense. So coevolution is an observable thing. And that's sort of the thing in the middle. Coevolution is the process by which design candidates are generated. It includes ideation, or is at least part of ideation. So, I took these three things and put them into a theory that looks like this. So, SCI Theory, Central Revolution Implementation Theory, posits that there is an agent, and that agent engages in three basic processes, sense-making, coevolution, and implementation, in whatever sequence the agent deems correct. So the agent doesn't necessarily do one and then the other, they bounce around, depending on their goals and what makes sense at the time. When I say that there is an agent, I don't necessarily mean a person. An agent can be many people, but working together in a coordinated fashion toward a common goal. As such, this theory does not describe distributed software development where teams are not very coordinated. You can have distributed software development where teams are highly coordinated, but you can also have distributed development where you have multiple teams who aren't really working together, or projects that are so large that they're being simultaneously constructed by different agents, different groups, who may have different political purposes or agendas. It doesn't describe open source projects that are developed by 100 different people, all of whom have sort of slightly different goals and objectives. It only describes projects that are developed by a single cohesive group. And that single cohesive group engages in these three things. This brings out two evolutionary loops. There's two iterative loops in this diagram. Okay? One is the rapid oscillation between your ideas of the context and your ideas of the solution. That's coevolution. That's something that happens in minutes or hours. It's something that happens in a room. You can see it and it happens fast. It also happens when programmers have breakdowns where they don't know what to do next, or something goes wrong. And they oscillate rapidly between sort of information they have about the problem and their code rapidly trying to figure out what to do. So coevolution happens fast. There's a slower iterative loop that involves the construction of the design object, the software, the artifact, the thing that you're building, and its deployment in the context, and then the subsequent revision of the design object. So this is prototyping. So the prototyping loop happens over weeks or months, or possibly even years, but usually weeks or months. These are two separate iterative loops that occur in the design process. You will notice that in the mental picture of the context, we have goals, constraints, and problems. We do not have requirements. This is because I can't find any. I know this is a very strange thing for some people in the room, but I can't find any evidence that requirements exist, and can find a very strong philosophical argument that they don't in most projects. I will not discuss that here, but we may discuss it in the discussion later. I don't want to get lost on that rabbit hole. But that's why this is not an omission. This is a conscious thing that I can't find requirements in the projects I'm studying, and that's why they're not there. This is a theory for explanation in Gregor's taxonomy of different kinds of theories mentioned by Per yesterday. It exhibits teleological causality. Pontus mentioned teleology yesterday. Teleological refers to an agent, refers to actions by an agent. So invariance theories, where we have a bunch of antecedents that contribute to a dependent variable, we have probabilistic causality. If these things are true, it increases the probability of something. This is a different kind of causality. Teleological causality is where you have an independent agent who can take actions in the world. Okay? So this remote just moved. Why did it move? Because I moved it. And I'm an agent with free will, and I can do what I want. So it moved because I moved it. That's teleological causality. This approach to causality is very useful in agent-centered process theories. It's not correct or more correct than some other approach. It's just appropriate in this context. Now, you can use this in a lot of ways. I've used it to evaluate and improve the software engineering curriculum. So the ACM publishes a model curricula for software engineering programs. You can use this to analyze the ACM model curricula for deficiencies. Doing that, I found that the model curricula does a great job of teaching sense-making. They never call it sense-making. They don't use that word. But there's all sorts of techniques in the software engineering curricula about modeling and domain engineering and requirement solicitation that are kinds of sense-making. Okay? And there's all kinds of good stuff about implementation, about coding and how to write tests and debugging and all that good stuff. But there's nothing about coevolution. Again, I wasn't looking for the word coevolution. I wouldn't expect them to use that word. But I was looking for design candidate generation. How do you come up with ideas for what to build? And we don't teach that effectively. We don't teach ideation, we don't teach brainstorming, not very well, not in computer science, not in software engineering. You can use this to evaluate and improve methods and practices. If you're suggesting a cohesive design method, something that's supposed to be complete, end-to-end guidance, and it doesn't mention sense-making, or I might call it problem framing instead of sense-making, or problematizing. It doesn't mention that. That's bad. That means that there's a big piece missing. Or if it doesn't talk about coevolution, not necessarily in those words, but there should be some mechanism for design candidate generation. You can use this to inform theories of software project success. If you have a very strange view, if you have an idealized view of the software process as occurring in a series of phases, where the first phase is analysis and the last phase is deployment, then that will often lead you to unhelpful views of success, where you start saying things like, if the intermediate documents in our process are good, that should lead to success. Well, that only makes sense if you see the design process as a series of cumulative phases, where the documents are main outputs of the design process. If you see it this way, then you start saying things like, well, probably how good we are at coevolution is a determinant of success. How good are we at implementation? That's a determinant of success. How good is our sense-making? That's a determinant of success. I've evaluated this in a few different ways. I did a survey of software developers where there was a scale, and on one side was ideas consistent with this model, and on the other side was ideas consistent with Jiro's function behavior structure framework, which is kind of like a generalized waterfall model. So you can take the waterfall model and you can draw it out with a highlighter on Jiro's framework. But his framework is sort of more general, more powerful, more iterative. And created a scale where it was sort of an agree-disagree kind of items. And if you agreed with the items, you were acting in a manner consistent with this. And if you disagreed, you were acting in a manner consistent with the FBS framework. And of course, some of them are reversed, just to catch people going down one side. And found that the distribution was unquestionably skewed to the direction of this theory. When this is not subtle. You don't need statistics to see this skew. It's way on one side. I evaluated it using case studies. Basically, the function behavior structure framework, like the waterfall model, like things like that, were inoperable in the case studies I did because there were no requirements. There were documents. There were things called requirements written on them. But a requirement is a necessary condition for success. It's not just anything that you want. It's something that is needed for the project to work. And either the things weren't needed for the project to work, or we had no idea if they were needed or not. They were just somebody's guess. And because of that, the actual requirements in those documents were radically insufficient to drive the design process. So this became a much better explanation of what was happening in the FBS framework. Also, coevolution, as I said, is an observable phenomenon. I have video of developers actually drawing two diagrams and walking back and forth between them as they change their minds about what's in them. It's a thing you can see. You can't see it in someone's head, but people don't always do coevolution on their own. They often do coevolution in groups, and they externalize their cognition into boundary objects in speech. And when they externalize their group cognition into boundary objects in speech, their coevolution becomes visible. A couple limitations on this. As I said before, it assumes that there is one agent. It does not attempt to describe development by more than one agent. Second thing is that it assumes that the artifact is complex. It assumes that the thing that you're building exhibits emergent behaviors. It's a complex system. If it's a simple system, you don't do this. If it's a simple system, you can go in a straight line because your analysis is trivial, you know what you're supposed to do, everyone agrees on what is to be done, you just get on with doing it, and you can move it in a linear way. So this does not describe simple development very well. It only describes complex system development. Also, this is only one perspective. Van de Ven and Poel wrote a paper where they talked about 4 different kinds of process theories. Life cycle models, like the waterfall model, evolutionary models, like the theory of evolution, dialectic models where there are sort of different groups with power and they fight over something, and teleological models where there's an agent who takes action in the world. And Van de Ven and Poel argued that to really understand a phenomenon, one should come at it from multiple perspectives. One should generate process theories of multiple ideal types to really understand, to deeply understand what the system is like.
Yep.
And that's the end of my talk. Thank you very much.